Welcome to the Methods Lab. In this new series, we study advanced data science pipelines in R and take a look under the hood. My name is Casper van Lissa. I will walk you through the code and teach you how to think like a professor of data science. The techniques you learn in the Methods Lab will help you turn questions into answers, data into decisions, and skills into better research projects. Today we're taking a look at a latent class analysis pipeline. It's a topic that I particularly care about because I authored one of the packages in R that allows you to do latent class analyses. It's called TidySEM or TidySEM. So what is latent class analysis? It's a technique that's also sometimes called a mixture model. And I always find it most illustrative to look at a very common sense, intuitive mixture model example. So when I teach a statistics class, I often give examples that start with a description like this. Grades are normally distributed with a mean grade of 6 and a standard deviation of 2. And I once had a student raise their hand and say, hey, maybe this is a stupid question, but are grades actually normally distributed? So we looked at the data and it turns out they're not. So here are some grades of 347 of my students. There is a histogram on the left and a density plot on the right, and both of these plots show strong deviations from a normal distribution. And specifically what we see is a bimodal distribution. So we see one peak followed by a second peak. So basically what we see is that there's a group of students who all failed and a group of students who all passed. And one way to think about this would be that there's students who know they're going to fail, so they didn't bother studying for the exam, maybe they're counting on the resit. And there's another group of students who expect to pass and they did study, and because of that distinction we see these two bumps in the data. And I sometimes call such a distribution a camel plot, and because a camel has two humps. And latent class analysis is a method that allows you to pull apart those two humps based on observed indicators in the data. So in this case, our observed data are just the grades. Every student received a grade, but we can see that there are two underlying groups, students who were going to fail and students who were going to pass. And I can learn group membership from the observed indicator grade. And doing so would be a latent class analysis. So we can relate latent class analysis to other types of latent variable techniques. Think of it as follows. You might be familiar with continuous latent variables, and if those have continuous observed indicators, we call it a factor analysis. So for example, if we administer a psychological questionnaire and we try to estimate the underlying psychological trait, that trait is a continuous latent variable or factor, and the indicators are people's responses to the questions, which could probably be treated as continuous as well. If you have a continuous trait, but the responses are categorical, for example, correct or false answers to a quiz, then we call it item response theory. And if we have a categorical latent variable with continuous indicators, we call it a mixture model or sometimes just latent class analysis. Historically, the term latent class analysis was also used to describe categorical latent variables with categorical indicators. So the basic idea behind latent class analysis is that we assume that our population consists of k subpopulations, where sometimes the number k is unknown and sometimes we have a good theory to expect a certain number. We then model our observed data as a function of unknown class membership. And the simplest model you can think of is just estimating a different mean for your different classes. When do we use latent class analysis? For example, because we want to test a theory about a categorical latent variable, or because we want to group individuals based on observed indicators, or because we want to know how many subpopulations exist in our sample, or because we want to know which items discriminate best between classes, or because we want to predict class membership from covariates, or because we want to predict outcomes from class membership. Now let's get to the case at hand. This is a project that I was involved in where a mental health care facility wanted to know whether the close family members of those in their care needed extra support when caring for their loved one who was receiving treatment. So at this institution, they administered a questionnaire to those caring for people with mental health problems. And based on that questionnaire, we tried to tease apart different groups with different support needs. We called this project the Care Compass, and the paper is currently in preparation. Now, the reason why I think this is a particularly interesting use case is because it allows me to showcase some of the new functionality in TidySCM version 2.11. And this is functionality that was not yet available when we wrote the paper. Initially, the idea was to distinguish these latent classes based on some continuous variables plus ordinal indicators, which reflected people's motivations for caring for their close other. So let's open our studio and have a look. So I made a simple script to walk you through the code. Now, to start off with, we want to import some dependencies. These are packages that contain functions we will use. First off, we use library TidySCM, which is my package for running structural equation models, including latent class analyses. If you want to follow along, you might want to install the development version from GitHub, which you do by running remotes install_github/cjvanlissa/TidySCM. I already have it installed, so I can just run library TidySCM. We're also going to use foreign because the data were created in SPSS, so it's a SAV data type. And we're going to run library OpenMX, which is the engine that estimates the structural equation models, and library Psych to do some psychometric analyses. So let's import all of these packages. Next up, we need to load the data. So because this is privacy sensitive data, I'm not going to show it to you. It's in a different folder, and I'm going to load the file from there and then read the data, do some renaming, and later we're going to construct a synthetic data set that you can use to follow along with these analyses. So first of all, what I always like to do if my data contains some scales is I will create a scales list with names corresponding to the names of my scales, and each of the elements of this list will contain the indicator names that belong to that scale. So if we look at the names of our data frame, which is called DF, then we see, for example, that there are these items that start with LON. That is the loneliness scale. And so what I want to do is just grab all of those from the names of my data frame and stick them in an element of my list called loneliness. So let's run this bit of code. And it gives me this scales list with 4 scales and each of the items that belong to that scale. So now I can do all kinds of psychometric analyses on the 4 scales in this data set. The second thing that I'm going to do is I'm going to drop all of the columns from my data frame that we don't need for this tutorial. So which columns do I want to keep? Well, I want to keep all of the elements in our scales list. I can just drop the levels again by using unlist scales list. And these are all the items that I want to keep. Then I'm going to grab the motivation items that are in the data frame. And I want 2 other variables, namely freq, which is frequency of visiting, and sex-C, which is the sex of the caregiver. And keeping just these variables leaves us with a much more manageable 47 variable data frame. Next thing I want to do is perform some psychometric analyses to see whether these 4 scales have acceptable measurement properties. So what I'm going to do is I'm going to use l'apply, which applies a function across levels of a list. For now, I'm applying a function to the names of my scale list. So I'm passing an argument nam, which stands for name. And then what do I do inside that function? Well, the first thing I do is call the function TidySCM on the columns of my data frame DF that corresponds to the items in the scale list with that name. So the first name is going to be burden. So this is going to give me the items belonging to the burden scale and the columns of the data frame corresponding to those items. Then I use the base R pipe operator to pass this TidySCM object to measurement, which constructs a confirmatory factor analysis model. Then I'm going to pass this to runmx, which calls openmx to estimate the model. And then I'm going to pass those results into an object called res for results CFA. Then I'll run the function tableFit to extract model fit indices. And for a confirmatory factor analysis, those tell me whether a one-dimensional measurement model fits the scale acceptably well. I will also extract the composite reliability using a function from the SEM tools package. And that tells me whether all of the items in the scale consistently measure the same thing based on their factor loadings. For those of us who like to see Cronbach's alpha, I can also use the psych alpha function. So I apply that to, again, the columns of the data frame that belong to this scale. And I will just extract the raw alpha from the results. So I know that the raw alpha lives inside of an object called total, which is returned as part of the output of psych alpha. So I just make that selection and get an atomic numeric vector. Next, I'm going to use the function table results to get the results from my confirmatory factor analysis. And I'm going to grab the absolute factor loadings. And I'm going to grab the absolute factor loadings and save the lowest one and the highest one. So basically here I'm constructing a table with model fit, latent variable reliability, and minimum and maximum factor loading so that we can judge the quality of the psychometrics of this scale. I'm column binding all of this information together with the variable name and doing that for all of the 4 scales in our scales list. So let's run this. And we get an error. And the error was undefined columns selected. And that happened when I tried to extract these columns from the model fit table. So why did we get this error? We got this error because I tried to be clever and run the model in OpenMX, but OpenMX does not return those model fit indices by default. So what I guess I should have done is run this in Latent, because that's what this code was originally developed for, and then also add Latent to the libraries here that I want to import. So now I also imported Latent. And if I run the model with Latent instead of OpenMX, then these model fit indices will be available because those are part of the Latent output, and this function should run now. Let's have a look. And again, we got an error. Why did we get an error? Because when I tried to take the absolute value of the estimates column of the results table, for those estimates where the operator corresponded to a definition operator, so these are the factor loadings, then I got non-numeric argument to mathematical function. So when I tried to take the absolute value, apparently I tried to pass it a non-numeric argument. And that is true because actually table results is meant for formatting objects as publication-ready tables. So it applies numeric formatting and just returns character type columns. In this case, however, I want the original numeric value. So I guess what I should do is turn format numeric off, turn it to false. So if I run that, then this function absolute should get numeric values as part of the estimate column, and it should be able to calculate the result. So let's try again. So I stop the debugger here, and I will rerun this block of code. Yes, in this case, all I get is warning messages, which is good news. So we're going to ignore these warning messages. What it's telling me is that some items are negatively correlated with the rest of the scale. And that is fine, because actually some of these items are negatively worded relative to the rest. So they should be inverted, and to do that automatically, I use the option check keys equals true. That means if an item is negatively correlated with the rest of the scale, then invert its values. So this is already taken care of, but I still get some warning messages to notify me. But otherwise, we did get our result. So if we look here in the environment, we now have an object called SCLS, or scales, which contains the psychometrics of these scales. And if I want to make a nice table out of those, then I can just do .call rbind to these scales. And if we run that, then we see it just row binds those 4 results together. And what can we learn from this? So first of all, let's put it in an object. Let's put it in the object tab scales, and then we can view the object over here. So these are our 4 variables. They give us models with different numbers of parameters because they each have a different number of items. We have a chi-square, which is the basic measure of model fit, degrees of freedom, which allows us to do a fit test, the CFI model fit index, TLI, RMSEA, and SRMR model fit indices. And basically what we see is that the model fit is quite poor because we want these to be above 0.90 or even above 0.95. So model fit is quite poor for burden and for loneliness. And model fit looks acceptable for the worry scale. These fit indices are both around 0.90 and perfect for the entrapment scale. But wait a second, we see that the entrapment scale has 0 degrees of freedom. And that happens because here we have a 3-item scale, and a confirmatory factor analysis for a 3-item model has perfect fit. In other words, we can perfectly describe the covariance matrix with our CFA model, so the fit's going to be perfect by default. So we shouldn't really read anything into these fit indices, and we just ignore them. The RMSEA should be small, I think below 0.08 or below 0.05. Well, it also isn't. And the SRMR should also be very low, and again, it's not. So in other words, these models don't fit very well. I actually know why this is. This is because each of these variables has ordinal indicators. And so we violate some assumptions by treating them as continuous. For the present example, that's fine, because that's not what we're focusing on today. But if these were your data, you might want to look into how you can model these indicators as categorical variables. And then your model fit will go right up. So what else can we glean from this table? We see that the composite reliability or latent variable reliability is good for burden. It's above 0.90. It's okay for entrapment. It's 0.89. It's low for worries, 0.68, and it's unacceptable for loneliness, 0.03. And Cronbach's alpha shows a much rosier picture. These all look pretty good. They're all above 0.80. If we look at the factor loadings, the smallest factor loading across all variables is around 0.80, which is still very good. And the maximum factor loadings range from 1.01 to 5.6 here. So if this was anything but a tutorial example, I would know that there's some more work to be done. But for today, we're going to ignore this. We're going to save this table to a spreadsheet. We're going to write it to a CSV spreadsheet, which is a nice text-based data type. And we're going to move on. Specifically, what we're going to do is we're going to add columns to our data frame df. Those columns will have the names of our scale list, and we're going to construct them by taking the row means of the data frame columns that belong to that element of the scales list. So we're calculating a mean score for all of the items belonging to each scale. So let's do that. And now we see that we have 4 more variables in our df. And then we can subset the data frame further to prepare a data frame for estimating our latent class analysis. So in this case, all I'm doing is retaining the 4 columns belonging to our burden, entrapment, worries, and loneliness scales. Now the next part is our latent class analysis, and it takes a long time to run, especially once we add the ordinal indicators. So in this script, I'll use a very rudimentary method to make sure that you don't accidentally rerun this super computationally intensive analysis. Specifically, what I'm doing here is I'm checking if a file exists called reslpa.rdata or results latent profile analysis.rdata. If that file does not exist, and this bang operator or exclamation mark means not in logical notation, then I want to run the analysis. And I will set a random seed, because this analysis depends on randomness, and run the function mxprofiles on the data frame for LCA that we just created, and I will ask for 1 through 6 classes. That will take a while to run, and when I get the result, I will save the object called reslpa in a file called reslpa.rdata. So because this one is still manageable, let's run it together. I will select all of this code and run it. So we get some notifications. It tells us which model it's running. So right now it's telling me that it's using simulated annealing to estimate this model. So what is simulated annealing? Simulated annealing is a method that helps you avoid local optimal solutions when you estimate a model. And this is really useful for latent class analysis, which notoriously tends to have many local optimal solutions, but only one global optimum. So there are different solutions to this. If you use the M+ commercial software package, for example, what it does is it tries a wide range of random start values, estimates the model for each of those start values, and then checks whether the set of best fitting models resulting from all these start values all have the same -2 log likelihood or model fit. If that's the case, then they conclude that you have found the global optimum. TidySCM works a little bit differently. First, it creates a deterministic clustering solution using hierarchical clustering. It estimates start values based on those deterministic clusters and then estimates the model with simulated annealing. And think of model estimation as a marble rolling around in a landscape looking for the deepest valley. Once it settles in a valley, the estimation is complete. And you want that marble to settle in the deepest valley of the landscape. That's the global minimum. What simulated annealing does is it lets that marble roll around the landscape, but occasionally it flicks it to a different part of the landscape. The idea behind this is that if the marble is in the deepest valley of the landscape, it will be hard to flick it out of there. But if it's in a shallower valley, then flicking it out might help it roll towards the deepest valley in the landscape. So that is what our estimator is doing. We see it's still running. I think that it takes a few minutes to estimate up to 6 classes for this analysis. So we just let it run and then we come back to this when it's done. A few moments later. Okay, so we're just gonna cheat, and like a baking show, I already have the results ready for you. They're in a drawer under the kitchen counter. I will just run this code and load the results from a file. So now we have the results for our latent profile analysis in memory. They are over here. It's a list of OpenMX objects. And what we're going to do is we're going to extract the model fit from these 6 models. And let's have a look at the resulting table, which we called tab fit for table fit. These are the model names. So we estimated an equal variance model with 1 up to 6 classes. Here we see the raw model fit in terms of log likelihood, the sample size, number of parameters, which we see as increasing with the number of classes. And then we get model fit indices AIC and BIC. These don't have an objective interpretation, like the CFI and TLI did. But here we just say that lower is better. And research has found that the BIC is one of the best functioning indicators for selecting the optimal number of classes. So if we just look here, then we see that the BIC would suggest a 5-class model. Now I have reasons not to prefer a 5-class model, and I will walk you through it. The most important reason is that if we look at this column NP local, it gives us a value below 10. So what is NP? The number of observations, N, per parameter, P. So this means that we have less than 10 observations per parameter that was estimated in this model. And that's not a lot of data points. So my concern is that this model might be quite overfit to the sample at hand because I have only a few observations per parameter that I estimated. I typically use a rule of thumb of a minimum of 10 or 20 observations per parameter that I try to estimate. So in this case, I would definitely not consider a model with 5 classes as my final solution. I eliminate it. If we venture a guess as to why a 5-class solution might be the best fitting one here, it could be because, as I mentioned before, the indicators are ordinal and they are Likert scales with 5 response options. So one thing that can happen in latent class analysis is that if you treat Likert type ordinal variables as continuous, then your analysis will prefer a model with a number of classes equal to the number of indicators, which basically means that every response option gets its own latent class. So that is one reason why you might actually want to treat these as ordinal and not as continuous. The disadvantage of doing so is that the number of parameters in your model really explodes. It becomes very large and the model becomes hard to estimate. So you kind of have to strike a balance between computational effort and faithfulness of the model to the data. Another thing we can learn from this table is whether the classes can be easily distinguished or not. And we can judge this based on the entropy criterion. So this is basically the inverse entropy, and a high value means perfect class separability. The model has no doubt whether each case belongs to class 1 or class 2 or class 3. And very low values mean that according to the model, it's basically a coin flip whether a person belongs to class 1 or class 2. So what we see here is that, of course, for the one class model, we have perfect entropy. That's no surprise. There's only one class, so there cannot be any doubt as to whether every observation belongs in that class. Then for the 2-class model, entropy is pretty high, 0.91, but it rapidly drops off from 3 classes onwards. In other words, the boundary between classes is kind of fuzzy and they overlap. So there's not much to go by in this table. What we see is that the model prefers an unreasonably complex solution with 5 classes, and even in lower class models, it's kind of hard to distinguish members of the different classes. Let us save this fit table to a spreadsheet so we can use it in a paper later. And now let's get to the heart of the matter. As I mentioned before, originally the researchers that I collaborated with wanted to know whether people's motivation for caring for a close other would weigh into their class membership. So to assess this, they included some motivation items. And these were questions like, I do this because I love the person, I do this out of a sense of obligation, I do this because it makes me feel useful to society. So these are all yes or no questions, and accordingly, we see that the motive or motivation items all have 0 or 1 values. So it's binary, yes or no, true or false. So what we're going to do is, first of all, we're going to identify which items belong to the motivation scale by using grep to take the items that start with the word motive from the names of our data frame. So if I run this, I get an object that contains the names of the motivation items. Then I'm going to construct a new data frame that contains the scales list names and the motivation items. I'm going to call that subsetted data frame df mixed. And then I'm going to recode the motivation items in df mixed. And I'm going to make them all of data type ordered. And this is important because the tidySEM package recognizes how it should model each variable based on its data type. So if it's a numeric variable, it's going to estimate a mean and a variance for it. But if it's an ordered variable, then it's going to estimate what's known as a threshold. And for an ordinal variable, that tells you what percentage of observations falls below the threshold and what percentage falls above it. So let's do that now. So here we made all of these items ordered, and we can confirm that in the environment up here. So we look at df mixed, and we now see that the 4 continuous scales are numerical, and all of the motivation items are ordered factors with 2 levels, 0 and 1. So now comes an obscenely computationally intensive analysis, which is the MX mixed LCA, and that is a latent class analysis with mixed data types, in this case continuous or numeric and categorical or ordered factors. I'm just going to pass this function the subsetted data frame, and I'm going to ask for 1 to 4 class solutions. Why 1 to 4? Well, because this analysis already takes a very long time to run, and based on the previous latent profile analysis, I know that a model with more than 4 classes has very few observations per parameter. Once I add the ordinal indicators, the number of parameters is going to increase even further, and I'm going to just run into convergence problems and my model will run forever. So I don't even need to estimate the 5-class solution onwards to know that these are going to be terribly overfit to the data. So I will actually not run this because it takes a long time, but I already did it overnight and I will load the results from a file. The second thing that I wanted to show you is another way to determine the number of classes. And this is using predictive model comparison. This is a method that we're currently writing a paper about. It performs very favorably to 2 best practices for determining the number of classes in latent class analyses, and those are selecting the lowest possible BIC and looking for significant bootstrap likelihood ratio tests. The BIC is a great method for comparing classes, but it doesn't give you a test, so it's hard to determine what cutoff you should use for selecting the best model. The bootstrap likelihood ratio test basically draws many bootstrap samples and then runs your latent class analysis on each bootstrap sample to get an empirical distribution for the likelihood ratio test. Now this is a problem because I just told you that the analysis itself takes maybe a half hour to run. If you then drew 1,000 bootstrap samples, it would take 1,000 times a half an hour to do the bootstrap likelihood ratio test. This is infeasible. It's also a waste of computational resources. So what we came up with is a method that is basically a quick and dirty alternative to the bootstrap likelihood ratio test. It performs on par, so we're going to use that here. In this case though, I'm still not going to run it. I'm just going to load it from memory. Oh, I can't. I forgot to save it. So we're going to actually have to run it. So that allows me to show you how this code works. If I select this code block, first it's going to check if a file with these results already exists. It doesn't, so then it's going to run this code and save it. So if I run this whole if statement, it's going to open up this progress bar and it's going to start calculating my predictive model comparison. And you see about how fast that goes. It's doing 100 iterations. Our predictive model comparison is finished and we can have a look at the results. So what do we see here? We see that compared to the 1-class model, the 2-class model fits significantly better. Compared to the 2-class model, the 3-class model does not fit significantly better. And compared to the 3-class model, the 4-class model does fit significantly better. So here it's a bit of a hard choice, right? Because you could say, well, I'm going to select the most complex model that still gives me a significant improvement in fit, in which case you would choose the 4-class model. Or you could say, I'm going to choose the simplest possible model that has a significant improvement in fit, in which case you would choose the 2-class model. I think you can probably already guess which one I'm going to prefer. It's the 2-class model. I'm going to prefer the simplest possible model with a significant improvement in fit. If we look at the other fit indices, we see the following. The BIC just keeps decreasing for an increasing number of classes, so that also suggests the more complex model is the better. But the local number of cases per parameter drops down to as low as 4. For the 4-class model, that is unacceptable, so I'm going to prefer the 2-class model, which has 16 observations per parameter. Also notice that the number of parameters is much higher now that I'm including all of these ordinal indicators. So let's proceed with the 2-class model, and we can inspect the model results in different ways. One way is to plot it using plot profiles. I can just select an element from my results list by numerical indexing. So here I'm taking the 2nd element from this list. And if I'm making a profile plot, I can only plot the continuous indicators. So I'm asking for the scales variables burden onto loneliness to be plotted. So let's plot that. And this kind of confirms what we already know, namely that these classes overlap a lot and they're hard to distinguish. And we can see that from the pretty low entropy, which means low class separability. So for burden, we see there's some distinction between the 2 class centroids, but they overlap a lot as well. For entrapment, we see pretty good separation. For worries, we see a little bit of separation, and for loneliness, we see a tremendous amount of overlap. We can also look at either a table or a plot of the probabilities for the ordinal indicators, so the motivation scales. So let's apply table prop to the second element of our results list. And then we see here for each variable what the probability is that a participant in each of the classes is in one of these two response categories. This is a little bit hard to compare, so another thing we can do is to turn this into a plot. So that command is plot probability. And again, we apply that to the same second item of the results list. And what do we see here? So the darker blue is response in category 2 and the lighter blue is category 1. So what we see is that class 2 has more people in category 2 for motivation 1, but fewer people in category 2 for motivation 2, more people in category 2 for motivation 3, and so forth, right? So you can compare these two classes in terms of how people are distributed across yes or no responses for each of the different motivations that exist. The final thing that I wanted to do with you is to estimate an auxiliary structural equation model where we compare these two latent classes on some auxiliary variable. For example, we might want to know whether these two classes differ in the frequency with which they visit the person they care for. The variable that measures frequency is called freq over here, and I can use the BCH function, here is its documentation, to estimate a very basic auxiliary SEM model for frequency based on the two latent classes. So let's do that now, and that's very quick. And then we can use a likelihood ratio test to compare different parameters of these two models. And in this case, we just want to know, do the two classes have the same mean, m, of frequency of visiting? And what we see is that the overall likelihood ratio test is not significant. So there are no significant parameter differences between the two classes in terms of frequency. And we only allowed the means to vary across these two classes, so the pairwise comparison is the same as the overall likelihood ratio test. Both are just for the means. Another question we might have is whether there are differences in the sex of the caregiver across these two classes. Now, sex, again, is a categorical variable. We can include it by defining it as ordered. So we do that here. And then we run this analysis. Now, because sex is represented as an ordered variable, we're going to estimate thresholds, which tell us the proportion of men and women in both of these latent classes. And again, we can do a likelihood ratio test to compare them. And here we again see no significant difference. So there are no significant differences in the proportion of men and women across these two classes. And that brings me to the end of today's expose. The last thing I'm going to do is to generate some fake data so that you can download this code from GitHub and follow along at home. And to do that, I'm going to place the derived variables first in the data frame. The reason for that is because those are not real data, so they're not privacy sensitive, and I can use them to better generate fake data for the indicators that belong to those variables. I'm going to use the synthpop package to generate these data. You can also use the works package, which contains a function called synthetic, but today we use synthpop. And I'm going to use the syn function, apply it to the data frame, and the method is going to vary. So for the first 4 columns, I'm just going to use the original value and not synthesize it. And then for all other columns, I'm going to use a random forest from the Ranger package. So let's do that now. And we're done. So now I'm going to write these data to a spreadsheet as follows. And the last thing that I'll do is comment out the way that the data were originally read. And instead, I'm going to add some code so that you guys can read the data. When you reproduce these analyses, read.csv, data.csv. I do not want strings as factors, like so. I should probably drop these 4 scale scores. So I just go back here and drop the first 4 columns Let's try again. Yes. And then let's see if our analyses also run with the fake data. So we'll just step through them again real quick. Calculate fake scale scores, subset the data frame, run the latent profile analysis. Okay, that seems good. Okay, so it looks like everything runs. I will save this file and then put everything on GitHub. So let me double check what all is in the folder here. So I don't want to upload these R data files, so I'm going to add them to the gitignore file here. I do want all of these CSV files to be uploaded, so that's fine. I think I can just initialize a Git repository here. Then I'm going to use my works package to create a GitHub repository. And I'm going to connect it to the local repository. And then I can use the function works git update, first commit, to push all of this to GitHub. So here's the resulting GitHub project page. If you want to download this for yourself so that you can reproduce the analyses or try to apply them to a project of your choosing, then you can click code and download a zip, which gives you a compressed folder that you can decompress on your computer. If you're more familiar with the Git command line interface, you can also use this link here to clone it to your computer. Let's verify that all the contents are there. Here's the R project file, which you can open in RStudio. Here is runme.r, which is the script containing our analysis code. And here is the data.csv spreadsheet, which contains synthetic data that allow you to run through the analysis. Now, if you're left with some questions, that's a good sign. Why don't you try to apply the techniques you learned today to a topic that you care about, and let me know how you get on in the comments. See you next time, and remember to check your assumptions, not just your p-values.